Good morning to everyone. This is Ragu Sasikumar. I am from South Korea. In South Korea, this is very famous tower like Seoul Tower, this name. Okay, today I gonna present my recently published paper from Nano Energy, dysprosium tungstate incorporated molybdenum disulfide as a hierarchically connected novel composite based piezoelectric nanogenerator for self-powered energy harvesting and smart mask for human breath monitoring. So this paper we published last month in Nano Energy, and then this work was very interesting. That's why my university highlighted in their website. This is my professor. His name is Byungki Kim. So we are working on different sensors for different applications like electrochemical sensor and then piezoelectric sensor, acoustic sensor. Okay. So this is my motivation. Everyone knows recently, like the last 2 to 3 years, everyone affected by coronavirus. Not only coronavirus, it's a different variation, like the Omicron, Delta variation. They affected in worldwide. It is affected in worldwide, not only in global economy, but also in human respiratory system. So in our human body, lungs plays a crucial role to reflect the overall human health monitoring. So this human respiratory rate is exceeding 27 per minute, like a breath per minute means it is like a symptoms like a cardio arrest. And then SARS-CoV, it is symptoms like irregular breathing and shortness of breathing. So in this point of view, we developed piezoelectric sensors for dual application. Like one is self-powered energy harvesting, another one is human breath monitoring. We developed a novel composite dysprosium tungstate incorporated with molybdenum disulfide. Okay, so this is overall schematic representation. Here, you can see that is a normal mask attached with our sensor. So this is figure C is like a layer by layer fabrication method of our sensor. So see the mechanism is the initial state is when you breathe, inhale and exhale, your sensor, it will go compression state and then releasing state. So during this state, it will generate the electricity. And then this is a normal characterization like XRD, FTIR, Raman spectra, and then BET surface area of the composite. From this characterization, we confirmed that our composite formation is successful. And then this is the morphological studies we did with FEACM. Here, you can see the image of a nanocomposite like figure G2I. There is some two different junction, like this is called heterojunction. This junction only helps to improve the electronic transportation of the inside the composite. Okay, this is normal piezoelectric characterizations. You can see figure A, there are in our composite, there are three different components like a dysprosium and then tungstate and then molybdenum disulfide. Here, we did with a different modified film. One that blue color is a PDMS, only polymer. It's a substrate. And then second one is molybdenum disulfide with a polymer. So compared to other modified film, our composite showed very higher voltage, piezoelectric voltage. Then we did with a different percentage of our composite. See here, 30% of composite is higher than that 40% of composite because due to the agglomeration of composite. And then we did with further piezoelectric characterization with a different loading and different frequency. You can see the result. When you increase the different loading and different frequency, your piezoelectric voltage response also increases. And then to further confirmation of piezoelectric effect, whether it is piezoelectric or triboelectric, we confirmed with to changing the connection like forward bias and then reverse bias. Here in forward bias, you can see that that a positive voltage is very higher than that bottom voltage, and then in reverse connection, it's like a reverse like bottom electrical energy. Bottom electrical peak is very higher than that top electrical energy, and then we calculated our sensor response time. It's like the calculator is response time is 100 milliseconds, and then so figure A to F is a AC current. So this current we can't use for a portable electronic device. That's why we converted into AC to DC current by using flexible bridge rectifier. You can see the G is like that first one is that insert figure, that first one is AC current, we converted into DC current. Further, this DC current we charge with different capacitors. And then we did with the power density. Okay, so this is my first application. We that sensor we connected with our human body with different parts like a finger bending 30, 60, and 90 degrees, and then foot tapping, walking, and then running. You can see from this result, we interestingly observe that our sensor can produce different voltages with different parts of the. It depends upon the parts of the human body, and then. So mask we are going to use mask we will wear is not like straight. It will be like a twist or bending. So that's why we did with this experiment like a twisting and bending. From this result, we observed that interesting results. Like our sensor, it does not affect with twisting or like a bending like deformation. And then we did with different humidity experiments. Why? Because when you wear the mask, inside the mask you will feel some temperature like 4 to 7 degrees Celsius within a minute. That's why we did with our sensor with different humidity. You can see the 10% to 90%. 10% is like very dry nature, and the 90% very wet nature. You can see even 90% of humidity, our sensor can detect the voltage, 0.14 voltage. So from this result, our sensor does not affect with different temperature and then different deformations. And then this is second applications, human breath monitoring. We did with normal breathing and fast breathing. As per literature survey, normal breathing rate of human is like 12 to 16. Here you can see different breathing rate of normal and then fast breathing and different voltages we observed. But we can't claim our sensor can distinguish normal breathing and then fast breathing from A to A and D. That's why we further confirmed with the FFT spectra. You can see that a normal breathing rate is normal breathing frequency is in, close to 0 compared to F spectra, like a faster breathing. So from this result, we can claim that our sensor can distinguish whether it is normal breathing or fast breathing. And then to further confirmation, our sensor really works during the breathing. So further confirmation, you can see the G figure. Without breathing, that noise voltage is like a 0.12 voltage, but when you breathe, our sensor can produce 0.62 voltage. And then this is like that H figure is like a single breathing, like inhale and then exhale. And then to further confirmation, we did with breathing with the nose and then breathing with the mouth. You can see the higher voltage response of like breathing with the mouth is then that breathing with the nose. And then this is the real-time applications. You can see this is our sensor film. When you tapping, it will generate some voltage. That voltage we converted into AC to DC by using bridge rectifier, and then that AC voltage, DC voltage we used for glowing LED. And then this is a secondary real-time application. You can see this sensor can produce a voltage like a AC voltage, and then we converted into DC, and then we powered this watch. Okay, this is a third application, breathing with the nose attached with our sensor. You can see the LED glowing is brightness is very low. Then the same experiment we did with the mouth, breathing with the mouth. Here you can see the brightness of the LED. So from this real-time demonstration, we conclude that our sensor can distinguish whether it is normal breathing or fast breathing by using brightness of LED. Okay, so this is a summary of my work. So first we developed a dysprosium tungstate with a molybdenum disulfide for a dual application like energy harvesting and then human breath monitoring. And then from the first piezoelectric characterization, our sensor can produce nearly 1.3 voltage, which is 2 times higher than that MoS2, molybdenum disulfide piezoelectric sensor. And then the generator voltages we converted into DC to charge the capacitors and then power the LED and run the wristwatch. And then at 90% of humidity, it showed 141 millivolt. From the FFT result that exhibit like our sensor, developed sensor can distinguish between the normal and fast breathing. Finally, we achieved the glowing LED brightness is low means that patient breathe from nose, and then more brightness means like a breathe from mouth, and LED turn off means is stop breathing. So apart from this sensor, we developed further different applications by using piezoelectric sensor. First one is IoT application. Second one is acoustic sensor to recognize the human human voice. And then these last two work is like under review. Thank you.